So now I'm going to introduce, so the forbidden zone is a big deal, right? This notion of sort of not being able to complete successfully a mapping from a continuous variable to a discrete variable, sort of recognizing that and using the forbidden zone to rescue ourselves from that problem, that engineering problem, is a big deal. We're going to remember that. So the second thing I want to talk about now is how to build a digital processing element. So that this slide will have the other thing that I hope that you'll take away from today, or the second of three things. We haven't got to the third thing yet. Okay, so a combinational device. So this is a definition of what a combinational device is, what we mean by the adjective combinational. It has digital inputs, and so those are inputs that obey this digital signaling discipline. Something that's lower than a low threshold will be treated by the device as a 0. A voltage that's higher than this high threshold will be treated by the device as a 1. That's what we mean by a digital input. Have a digital output, in other words, it will produce signaling voltages that meet this specification. It has a functional specification that I can interpret the inputs as being either 0 or 1, or don't care, in which case the device can do anything it wants. But if all the inputs are in the valid digital signaling range, then I can make a big table that lists for all the different possible combinations of the input. So I have 3 inputs here. How many different combinations of the digital inputs are there? In other words, if I think of each input either being 0 or 1, altogether, how many different combinations do I need to consider? 8. Okay, so the A input can be 0 or 1, and the B input can be 0 or 1, and the C input can be 0 or 1. That means I can have either 8 possible combinations of those 3 zeros and 1s, 2 to the third. Okay, so I could make a table that had 8 rows that listed all the combinations of 0 and 1, 3 combinations of 0s and 1s, and then for each of those combinations told you what the value of the Y output was. That's what I mean by a functional specification. And the third thing, which we won't talk much about today, but will become more important to us next week, is I would also include a timing specification saying, once the inputs are stable, how long is it until the answer is produced? And at a minimum, we require the specification give us an upper bound on how long I have to wait. This magenta box will produce an answer within 1 second of having all the inputs become stable and then remain unchanging after that. In a digital sense, remain unchanging. Okay, even though their voltages may be going down a little bit up and down a little bit because of noise, it would still be the case that they were stable 0 or stable 1 according to this specification. Okay, and altogether we're going to call this the static discipline. So we're going to start, I'll say static discipline a lot, and you'll know what I mean now as these 4 different criteria. Digital inputs, digital outputs, a functional specification, and a timing specification. Okay, so if I give you a whole box of combinational devices, if you hook them together such that no input or no 2 outputs are shorted together and there's no cycles in the graph, I claim that the resulting device is combinational. Let me spend a quick moment and outline that reasoning. Okay, so I'm going to draw a very simple box circuit here. These are 3 combinational devices that have some inputs. And I claim that each of these guys is combinational. But now I have an acyclic connection where I'm not shorting any outputs together. I claim that that dotted box is also a combinational device. What's a good argument to make? Let's run through the argument about why it is. So what are the 4 criteria for a combinational device? Does this combo device have digital inputs? Yes. Why? Well, these guys all have digital inputs, and these wires are just going to these guys, so they're okay. Does it have a digital output? Yes. I mean, here's the output. It's coming from this guy, so this is sort of, by construction, it had a digital output. Same with digital inputs. Can I give you a functional specification? Is there a way I can derive the functional specification for this guy, given the functional specifications for each of the devices? And the answer is sure. I'm going to start off, I'll put zeros in each of these guys, and then I can figure out what's on this wire and this wire, and now I can figure out what's on this wire, and now I can figure out what's on this wire, using the functional specifications of each of the building blocks. And finally, and this we spend a little bit more time on this next week, it's clear that if I had timing specifications for each of these, I can come up with a timing specification for the whole thing, just looking for the longest path through the circuit. Okay, so that's sort of neat, right? This is the start of an actual engineering discipline that once we have devices that obey this static discipline, we call them combinational devices, I can build collections of arbitrary size that will still qualify as a combinational device, sell them to you, and you can include them with other devices from other manufacturers and still build yourself an ever larger combinational device. So we really have this sort of tinker-toy principle working for us, assuming we can do the engineering to actually be able to build a combinational device. So the rest of this lecture and the next lecture will be talking about how to actually glue together electronic components to make combinational devices. Assuming I can do that, what I hope I've convinced you is I finally come up with an engineering discipline that will let us sort of build things arbitrarily large. Okay, so let's deal with this real world problem, which, you know, we're going to have this sort of generic thing called noise, which represents all the bad things that happen to voltages as they go from one place to the other. And the question is, does a wire obey the static discipline? Is a wire a combinational device? If I sold you a box that basically just had a connection between one terminal and the other with a little piece of copper wire and said, it's a combinational device, would you buy it from me? You know, I have opened my raincoat and offered to sell you this thing. Okay, so, you know, that's always been the comic strict view of that. People don't seem to wear raincoats anymore, so I don't know what the motto. I know I'd put up a website and offer to sell you. So that, okay. So what we have here is this idea that, okay, suppose I have a legal voltage here, and I'm about ready to transmit it down. So this is a voltage axis here, not a wire. This is a voltage axis. And what I'm trying to do is the input voltage is just below this magic VL threshold. Okay, and then I get to the far end and noise happens, and what's happened is, you see this little guy here? He's moved. See, he's moved over a little bit because of noise, and now he's illegal. In other words, somehow this, you know, the notion that this noise is happening means that the poor wire is being victimized by the noise, and it can take an illegal input voltage, but because of the things that happen between his ears, okay, what comes out isn't quite right, isn't valid anymore. That happens to a lot of between ears around here, I've noticed. You know, I spend a lot of time putting things into your ears. We'll see how valid they are when they come out. You're not a combinational device. What can I say? I know, I'm using analog. Actually, if I'd given you everything digitally, it probably would have worked better. You know, deep educational philosophy. Right? On the fly, no extra charge. Okay, so we have this notion of noise, and what it can do is the simplest possible combinational device, or candidate for a combinational device, clearly isn't, because in the process of doing its job of getting the voltage from one end of the wire to the other, the trouble is that a valid voltage has become an invalid voltage, and you know, that's not supposed to happen in our system.